Hi, I'm Emma Lanceedle.
I'm Jared Howe.
This is our final project for 421L. Today we're going to be talking about kinematic constraints and why they're important for optical systems in allowing them to be uniquely defined in space.
So when you manufacture a precision optic, you have to mount it to something. You have to assemble it. And often the mounting has to be in a very precise location in order for your optical system to work within the required specifications. So kinematic constraints provide a level of adjustment and a level of repeated positioning down to often micron or submicron levels that are so important in precision optical systems when positioning your optics.
So the best way to get these sort of precise locations and repeatable locations is through kinematic constraints. So a kinematic constraint is defined as being a constraint that it's perfectly constrained but not over-constrained or under-constrained, which means that it will always have one unique position it goes back to. So now we're going to show you some simple models of that, and then also some more complex three-dimensional ones, and then finally an experiment we've done on repeatability to prove that kinematic constraints are indeed repeatable and reliable. So I'm going to talk a little bit more about how 3D constraints work. So in three-dimensional system, there are 6 degrees of freedom. Translation in the X, Y, and Z, and rotation about each of those axes as well. By adding one additional constraint, you can constrain one additional degree of freedom. So this is our simplest constraint. It only constrains in one direction, the X direction. By adding an additional constraint, you can constrain in 2 directions. And as this goes on, you can get more and more complicated until you have systems like these. You can count there are 4 constraints, which constrains in X, Y, and Z, and also in rotation about the Z-axis, which points this way. To fully constrain a system, you need 6 constraints. As you can see in these final examples, they are all different from each other, but they're still fully constrained since the constraints shown are not repeated, they're unique, and they also do not allow translation or rotation in any direction.
So in practical optical systems, there are several different types of common kinematic constraints, but 2 of the most common ones, I'll start off with the first one, is the 3-ball and 3-groove orientation. So this is one example. You can see that there are 3 balls. In an optical system, you can pretend there's an optic mounted to this surface on the back here, and there are 3 grooves. I'm talking about the grooves here, here, and here in this case. So each point of contact, each sphere has 2 points of contact due to the groove. That means that total there are 6 points of contact, and this just so happens to be a kinematically constrained system because it constrains all 6 degrees of freedom, and this top plate no longer moves. So you can actually see this again with this setup here. This is the 3-groove setup that I'm talking about, and if you pretend that this is some sort of optical mount, you can place the balls in the grooves, and you now have 6 points of contact, and this will no longer move. It's kinematically constrained.
And you can see it's constrained because when you have this one, you can still rotate, but you're constrained from translating except in one direction. You add this additional constraint, and all you have left is 1 degree of freedom in this rotation, and then by having, this final constraint, it is also constrained in that direction.
Correct. There's another main type of constraint that you see a lot, and that is the cone, groove, and flat. In this case, the cone is not a cone, but rather a set of 3 balls, but the principle is still the same in that it provides 3 points of contact for the first ball. The groove provides 2 more, so that's 5 so far, and then finally the last ball rests on a flat, which is 1 point of contact and is the 6th point of contact, perfectly constraining the system, and you can see that this optical mount no longer moves. So those are some of the main types of kinematic constraints. There are a bunch of others which are tested on these plates here, and we were in an earlier lab testing whether they were over-constraining or perfectly constraining or under-constraining our optical systems. So some systems require 1 or more degrees of freedom to be not constrained in order to allow motion that is required for its function. For example, say you have a laser scanner or a laser printer, and the laser is mounted to this tip here, and you want it to scan along this line of translation but not move up or down. What you need then is an arm that is also free to move along a vertical axis so that it can lengthen and shorten and keep that laser on that line of translation, but within the plane of its scanning.
So basically, it's really important to understand kinematics and how you can manipulate them to get the features you want in a mount so your system performs as required.
Go.
So now we're going to talk about how kinematic constraints can relate to mounts, especially for optomechanics. So this is a simple tip tilt stage, but when you take it apart, you can see that it is constrained by a ball in a cone, basically a part of a sphere in a V, and then a part of a sphere on a point. So that perfectly kinematically constrains it, and that means, in theory, this should have one specific location only for each turn. So basically, if you turn a certain mount and turn it back, it should go back to the exact same place. So in our experiment, we're going to test the repeatability of these mounts.
So for our experimental setup, we're using a mount similar to the one Emma just showed you, but a bigger one. It has the same interfaces with the balls and the cone, the groove, and the flat. We have two digital indicators that read down to a resolution of 500 thousandths of an inch. And we also have on the back two adjustable micrometers that read down to the 1/10 of an inch. So for every trial, we're going to move on the micrometer a 1/10 of an inch and move it back, and the indicator will tell us how far off from the original position that the mount has moved. And we're also going to read both indicators for each trial while moving only the bottom micrometer, only the top micrometer, and then both micrometers to see if there's any difference between the two. So for each trial, first Emma's going to change each indicator to 0. They're very sensitive. Then she's going to change the bottom micrometer by a 1/10 of an inch. Then she's going to change it back to its original position. And now we read how much each indicator has changed.
So now we're doing our test where we move both indicators at the same, or both adjustments at the same time and view the indicators. So in this case, we really wanted to make sure our procedures were the same. So we first move our top micrometer, so it's displaced by 1/10 of an inch, and then move the bottom one. And then we made sure to do that same direction when moving them back. So again, starting with the top and then the bottom. And by keeping this consistent, we made sure that we had the same procedure for each trial we did. And so we knew that our results would not be due to our procedures. So here are results from our experiments. We took 10 data points at each and averaged them, also found the standard deviations. As you can see, the upper micrometer seemed to have a lot larger readings than the lower micrometer. This could be to a lot of various reasons. The indicator may not be as precise, the kinematic interface may not be as perfect, or the mounting might not be as stable. But also, more importantly than that, you can see that the standard deviations are very close to the average values. So this indicated to us that we're probably close to the resolution limits of our indicators. So we don't really know where the error is coming from, since the indicators couldn't measure finely enough for us to see that.
So there's another potential reason why our standard deviations are so close to our averages, and that could be because there are a lot of sources of error that we didn't anticipate or didn't know about. One of them, the first, could be the obvious one, that we weren't able to exactly recreate the original position on the micrometer, and that resulted in just an inherent error in the position. So there's a lot of other reasons. There's so many moving parts that came with our setup. We were careful not to touch the table while we were making measurements, so the vibration in the table probably was not a factor, but the rail could have been moving a tiny amount, the stage, the mount itself could have been shifted on the stage. We have magnetic bases that could have been shifting slightly, along with arms that were connected with joints, and those connected to the indicators themselves. And these indicators are so sensitive that all of these moving parts could even be changed with air current. I can see them changing right now and I'm not even touching them. So those were other potential sources of error that might have affected the repeatability of this experiment. And putting all other errors aside, the error that we're actually testing in this experiment is the error in the kinematic interface of the mount. So any manufacturing error that could have happened, whether it be the balls not being perfect spheres and not having point contacts with their interfaces, any error in the shape of the cone, the shape of the groove, anything like that, errors in dimensions and material properties, all of that goes into the errors in the kinematic interfaces, and that affects the repeatability, making it impossible to be zero. So to sum up the presentation that we've given today, we first went through why kinematic constraints are important and the common types of kinematic constraints that are used in optical systems, and why in certain systems you might need some degrees of freedom left unconstrained to allow the motion that you need for that system. And then we also went through an experiment that showed a mount that uses kinematic constraints and how the repeatability and precision positioning is allowed by those kinematic constraints, and how there are certain errors that can affect the repeatability, but that in general it can be a very, very precise positioning system.
And to make improvements to this experiment, we would have as few connections as possible to both the mounts and the indicators to make sure they're not moving or changing position while taking the measurements, because we think that may be a source of our error. We'd also like to test maybe some lower quality and higher quality mounts to see what their performance is compared to this one that is clearly really high quality. And then just kind of experimenting with other mounts would be interesting as well, other than the tip tilt stages. We thank you for your time and have a great finals week.